Assalamualaikum and very good day to everyone. I'm Intan Zarahmat Darus and today I'm going to talk about system identification. I'm going to focus on least squared estimation and how to write the Matlab programming for least squared estimation. I'm going to also explain to you the derivation of recursive least squared and how the recursive least squared is written in Matlab to do system identification of an unknown system. Okay. Before we can actually write the Matlab programming for our least squared estimation, let's have a look at the model. Let's consider this system. Okay, we have a system with an unknown transfer function, and we're going to estimate, or we're going to assume the transfer function is Arcs model presented by this transfer function of b over a, the polynomial of b over a. Okay, and the system input uk is applied to the system and the output yk is collected as the system response. Okay, but however we have a noise applied to the system, zeta, that you can see from the slide here. Okay, so that zeta is actually as an input to a transfer function of 1 over a. Therefore, if you write the mathematics derivation of the system here, you can see that yk is equals to b over a multiplied by uk plus 1 over a multiplied by zeta k. Okay, that zeta k is actually the white noise to the system. Alright, so if I further improve, or if I further rewrite the mathematics by applying a to yk here, okay, but by applying this a, okay, I'm going to actually simplify the mathematics of this equation. It's going to become ayk is equals to buk plus zeta k. You can see that a 1 over a and our polynomial a here has been cancelled out. Therefore, we left only with zeta k, which is a white noise to our system here. Okay, let's say this is the model that we're going to use. Right, when I actually replace the a and b with polynomial, for example a, if let's say I want it to be parameter a is a Arcs model with model order n. Okay, so a will be 1 plus a1 z minus 1 plus a2 z minus 2 plus a3 z minus 3 plus until an z minus n. Okay, and that will be equals to uk equals to b1 z minus 1 plus b2 z minus 2 plus b3 z minus 3, and so on and so forth until we find the model order. Let's say the model order is n, until we find plus bn z minus n. Okay, before this class, I've already shown you in the slide before, in the video before, that the polynomial is then written in form of phi. Okay, but however today I'm going to consider that phi, okay, as a row matrix. So instead of having the whole lump of phi, okay, we're just going to have the row matrix of phi. So for example, for value of k equals to 1 or k equals to 2, okay, so what is the row matrix that actually describing that equation? So I'm going to assume that my equation is going to be rewritten in terms of yk is equals to x transpose phi, x transpose beta. Okay, that x transpose is actually similar to our previous video, which is a phi. Okay, however it is just one row of phi. So if you remember on the from the previous video, we have derived phi, isn't it? Okay, where we have yk is equals to phi multiplied by beta. Okay, but today, instead of having the whole lump of phi, we're just going to talk about that phi as one row, and that one row is x transpose that I have here. Okay, so if I further write that equation here, okay, what I'm going to have is, I'm going to have yk is equals to, alright, so why do I have that is because I'm going to expand this equation, okay, and that equation is going to be expanded into this form. Alright, I'm going to have that as yk is equals to, so if you look at yk, if you multiply it with 1, that's going to give you yk, but if yk multiplied by a1 z minus 1, that's going to give you yk minus 1. Okay, a1 yk minus 1. So that yk minus 1, I'm going to bring that to the other side, is becoming negative. Okay, a1 yk minus 1. Okay, so if I have a2, that's going to also give me negative a2 yk minus 2. Okay, and I'm going to have that until I have minus a(n) yk minus n. Okay, so that's what's going to happen. So similarly, on the other side, we have uk. If you multiply with b1 z minus 1, that's going to give you uk minus 1 with the b. If I can put this in this form, okay, I can rewrite it again, this equation. It can become a matrix of, as you can see in this slide, the matrix will be yk is equals to negative yk minus 1 until the data can be rewritten until we have negative yk minus n, which is your model order, and then you're going to start with uk minus 1 until you find your uk minus n. Okay, right? Then that will be multiplied with your beta, which is a1, a2, a3, and so on and so forth until you find your an. And then similarly, b1, this is supposed to be b1, okay, b1, b2, b3 until your value of bn. Okay, so then this, the whole lot, if you multiply with this, you're going to have your yk. Okay, that's how you're going to have a look at this. That's how you describe this mathematics of this system, okay, using ARC's model. Alright, so if you look at, if you remember the previous value, okay, so if you remember from the previous class, I've mentioned that this value yk, if you start, for example, with the value of k is equals to 1, what happens is that this is going to be y1, isn't it? Okay, but that one is going to be y0, negative y0. Okay, when we want to write this program in Matlab, Matlab will not understand matrix with the value of our discrete value of y0. It will not understand that. Similarly for y2, yk minus 2, yk minus 2 will give you negative y1, y minus 1. So similarly, Matlab will never understand what it means by y minus 1. Okay, so the minus 1 and 0 is not understood, okay, by Matlab programming. Similarly, for if you have that value here, k minus n, that's even worse, isn't it? Let's say n is equals to 5, okay, so that value will give you k equals to 1 minus 5. That's going to give you negative y minus 4. So that will be also negative value, which cannot be understood by Matlab programming. So what we do is that previously, if you remember from the previous class, we shift the data by 1. Okay, so when we shift the data by 1, your yk here become yk plus 1. Okay, that first part will be yk, okay, which is good. Now it's not going to be, when we have k equals to 1, for example, that will not give you 0 value, isn't it? Okay, which is good. That will be 1 value. This is going to be 2 and this is going to be 1, which is good. Okay, but what happened to the last value here? Let's say we have our n is equals to 5. Okay, the model order of our system is n equals to 5. So what happened is that that part there will become negative value again. All right, so it will not solve the problem if we shift the data by 1. So when we have the value of k is more than 1, so let's say we have n data here. Okay, so k will start from k equals to 1 until k equals to n. If we put that in our matrix form, we're going to have y2 until yn plus 1. Okay, and then our matrix, we have more row now. Okay, because our k have increased from just 1 until n. So when I fill in the matrix, this is what the matrix that I'm going to have. I'm going to have y1 until y2 minus n, and then on the column here, it will end up with negative y with capital letter N, okay, with n data. All right, so what is the problem with this matrix, guys? So if you look at this matrix, what happens is that when you have value of k equals to 1, with, let's say, model order n is equals to 5, okay, so what happens is that your value will be your matrix will be having 0 and minus. Okay, so what you're going to have is undesirable for your MATLAB programming. So you cannot write your MATLAB programming for this system identification using least squared if you have the value of your matrix 0 and minus inside it. Okay, so shifting by 1 will not solve the problem as we have earlier in the previous example I showed you in the previous class. We can solve the problem by just shifting by 1, because during that time we consider our model only model order n equals to 1. But now we cannot solve the problem as simple as that. Okay, and in fact, if we have more data, okay, in the previous class you've seen that I only give you 1 until 4 data, 1 until 10 data. Okay, so that is simply solvable, okay, by just shifting the value by 1. But if we have more data, okay, like in this case we have n data, okay, n can be as many as 1000. Okay, so you know already from previous knowledge, I've already explained to you that identification can be much better, prediction can be much better if the more data you have. Okay, the more set of input and output that you have, of course your prediction will be much better. Okay, so in this case this metric is correct, however it will not be able to be used in MATLAB when we have this negative value here. Let's have a look. Let's say for this part here I'm going to have negative y. Okay, if my n is equals to 5, 2 minus 5 will be minus 3. So a negative data will not be able to be used in MATLAB. Okay, so I need to do something about it. All right, let's have a look what to do about it. Okay, so initially this was our slide, was our model, our mathematics. So I have x transpose multiplied by beta here for my y. Okay, but we shift by 1, it does not solve the problem. Let's shift it by AND model. All right, AND model. Okay, so let's say we have the model order is n equals to 5 or n is equals to 10. Okay, so you need to shift that data by the model order that you have. Okay, so not just by 1. So if I shift the data by nth order, all right, so I will have yk is equals to yk plus n. Okay, so for yk minus 1 is going to be yk minus 1 plus n, and then you'll see that it at the end of the data y, you're going to have the last data, the last bit, instead of, you see here we have yk minus n. So that yk minus n, if I shift by the value of n, it will give me a value of negative yk. All right, similarly the same thing happened with uk. All right, so instead of having uk minus 1, when I shift it by n, it will give me uk minus 1 plus n. All right, and that will go on until we find our model order here. Okay, uk minus n will become uk. All right, so that's how our data is shifted when we shift it by 1. Okay, so what happened is that when we shift by 1, that shift by 1, it will not solve the problem. We need to shift it by nth order. So if we decide our n is 1, then of course shifting by 1 will solve the problem. But if our n is more than 1, it's, let's say it's 5, then we need to shift the data by 5, or we need, for example, n is equals to 10. All right, so we need to shift the data by 10. Okay, so that will solve the problem when we have a different higher model order, right? But what if we have higher model order, at the same time we have many data, we have 1000 data? You need to put all that value, all that data in your matrix form. Okay, so if I put the value just now, yn plus 1 until yn plus n. Okay, similarly we're going to start with k equals to 1 until k equals to n. All right, so this is the matrix that we have. So what is the problem? You look at what happened at the last row here. Okay, you will start to have value of negative. Okay, so when you look at the row, it will not solve the problem. Okay, because you're going to start to have a negative value because your data is not enough. Okay, so similarly over here, all right, let's say you have 1000 data. The last part, the last bit there will be n plus n. Let's say you have a capital letter N, the data is 1000, and the model order is 5. Okay, So if I put that value, the last value there will be y is equals to 1000 plus 5. So that's going to give me 1005. Okay, so what's the problem? The problem is the data that you have is only 1000. Okay, so you cannot have that 1005 because you simply do not have that data. All right, so this is the problem that you have, that you need to actually do something about it so that your MATLAB programming will be better. Okay, so hence if we have n data, okay, no matter how many data you have, let's say it's a n data, you need to shift the equation by, the first one is by your model order. Okay, if you have model order higher than 1, of course you need to shift the data by your model order, and then okay, shifting by that model order will solve the problem, but you cannot use all your data. So when you do your iteration later on, when you put your MATLAB, when you put your least square in MATLAB programming, okay, you can write your least square estimation using value of k from k equals to 1 until k equals to 1, n, capital letter n data that you have minus your model order n. What does it mean? It means to say if I have 1000 data, I'm not going to use all 1000 data. I'm going to use the first data until 1000 minus my model order n. So let's say my model order n is 5, then it have to be the data that I'm going to use is from k equals to 1 until k equals to 1000 minus 5. So I'm just going to use 995 data, okay, for my estimation. So the last 5 data will not be used. Why? Because simply the matrix will actually, when you use that 5 extra data, your matrix will require you to have more data. Otherwise, it's not going to be enough. Okay, so when we put this information back in our matrix, okay, so this is the initial matrix that you have. All right. Okay, so first and foremost, when you have this matrix, you need to know what is your model order. If it's model order equals to n, all right, so no matter what is n, for example 5, 10, 20, 4, okay, so you need to shift your data by having k plus n. That's the first one. Okay, then when you already have the whole data, the whole number of data, 1000, 2000, 4000, okay, data that you have, you're going to start your iteration, okay, for your to develop this matrix in MATLAB. You're going to use iteration. Okay, so you're going to start from k equals to 1 until k equals to capital letter N, the data that, the amount of data that you have, minus the model order that you have. So if you have k equals to 1000, sorry, capital letter K here, you have equals to sorry, not capital letter A, capital letter N, okay? Capital letter N here is equals to 1000. Then let's say your model order is 4. You're going to use model order 4. When you do your matrix, you're not going to use all 1000 data. You're going to use your data from k equals to 1 until k equals to 1000 minus 4, which is 996 only. Okay, so when you do that, what happened, guys? You will look at your metric. It will be adjusted so that the last value here is yn, not yn plus small letter n anymore. Okay, like what we have in the previous slide. So if you look at the previous slide, so that part is actually the problem, isn't it? That part will give you capital letter N plus the model order. All right, so the number of data, if it's 1000 plus the model order is 4, then you need to have y 1004, which you don't have because your data is only up to 1000. Okay, so by doing this, by just selecting the data, limiting it to n minus small letter n, okay, you will stop at the data that you have. Okay, similarly in your phi, okay, in your phi matrix here, this is a phi matrix. All right, so what you have is that you already do a little bit of modification, as I mentioned earlier, okay, so that your matrix will always have positive data. Not positive in terms of the value is positive, but the data, the discrete data that you're going to use is the having value of 1 and above. Okay, so the yk, the k value will not be negative or 0. All right, so then using this information, we're going to put that in Matlab, and then we're going to use Matlab programming to actually do system identification for our least squared estimation. Okay, so with that derivation, we can later conclude that for least squared estimation, this is we're going to use as previously y is equals to phi multiplied by beta. Therefore, the least square estimation is equals to beta is equals to phi transpose phi with the inverse of that, and then multiply by phi transpose of y. So from the previous slide, we have actually derive, okay, our y is equals to y starting from n plus 1 until yn, and our phi is the huge matrix that we have here, and beta is actually this value, and it depends on the value of your parameter or of your model order. So if you decide the model order that you have is going to be 2, 3 or 5, so the beta size will be double of that, because you have 5, for example, for A, and then 5 for B. Or if you have model order 4, you can have 4A and 4B. Okay, so using this least squared estimation, we later write our Matlab program. So if you have seen Matlab before, so when we open Matlab, all right, so this is the screen that we're going to see. Okay, so you can see actually there's a lot of information in Matlab here. Okay, so what you have is that this part here, okay, is going to show you the current folder. All right, this part here is the current folder that you have. So whatever folder that you open, okay, in this case I'm opening the folder of system identification, so that all the file inside that folder will be shown and displayed here on your screen. Okay, so another screen is important that you have is the current window. The current window where you write all your programming. Okay, you can write one by one your programming here, or you can also save your program using M file. Okay, so you don't have to write it again and again. Okay, so then you can just run your M file. Okay. All right, on the other side here you have workspace. Alright, when you actually run your program in Matlab, this workspace will actually give you all the parameters that you have actually used in your programming. Alright, so later on you see when we start to run our least squared, all these parameters will be shown here in the workspace. Okay, I have took the liberty to write the least squared estimation using my M file. So I'm going to open it for you. Okay, so what I'm going to do is actually when I open it later on, I'm going to run and show it to you how it works. Okay, I can just open the M file from my folder by double clicking the file that I have. So when I double click ls.m just now, okay, my M file will appear here. Okay, my current window is actually moved to the bottom here. Okay, so you see, this is how I write my program. Right, first and foremost, I'm going to normally when I write my program, I'm going to write clear first. Clear is just simply clearing my workspace. So if I have previous program that I run, okay, and I have previous parameter in my workspace, when I type clear here, it will actually clearing all my data in the workspace from the previous exercise. Okay, when I type close all here, it means to say I'm going to close all the figures that I have in my slide, so in my workspace. So if I actually plot any figures, it will close all. CLC here is actually just simply cleaning the screen. Okay, so if in the command window previously I have any program that I write on my command window, it is actually going to clear the screen by just typing CLC. Alright, when I want to load the data, when I want to use system identification, I need to have data, of course, right? So what I did is that I have my method, I have my physical system in my laboratory. Okay, I have flexible beam. Okay, what happened is that I apply some force to the flexible beam, and then I collect the response of the beam or the displacement of the beam Okay, so this force and displacement is the input and output of my system. Okay, so I already saved that input and output in this file mmj2213_01. So it's already in that file. Okay, and that file, it happened to be in the same folder that I have here. So where is it? So you can see that that file is here, .mat. Okay, so when we have the file in the same folder, then when we run, it will immediately read the value. Okay, so we can just type load there. If you don't have it in the same folder, you have to write the whole address, okay, of load. So in Matlab, the most beautiful thing about Matlab is that if you do not know how to load data, you can just simply type here help load. Okay, so when you type help load, what happens is that Matlab will actually explain to you all the value, all the way of using, okay, the description on how to use the function load. Okay, so in Matlab is very easy. If you have any function that you do not know how to use it, you just type help space and the name of the function that you have, and Matlab will explain to you how to use it step by step, as you can see here, okay, in the command window. All right, so you want to save, or you want to clear, or you want to import data, and also all you have to do is type help space and then what is the function that you want to know more. Okay, so now I'm going to clear the screen. I'm going to type CLC when I clear the screen. Okay, so that's gonna clear my screen. All right, let's have a look again at our M file least squared here. What I do is that I then plot the figure. So I name that figure as figure 1, and I plot my data. I have the time TT. Okay, X is the input of my data of my system, and again I have TT, which is the time. Okay, and Y is the output of my data. So what I did here is that I want to plot in the same figure both input and output data. Okay, and I'm going to plot it against the axis in this plot is time, which is TT here. Okay, so later on when I load the data, you will see that you have the data TT already. So maybe I can just load that one. Okay, so when I load the data, okay, when I run just now, okay, I'm actually loading the data. Okay, so when I load the data, you can see in the workspace, these are all the value that I have. So that TT here is showing that I have 6,000 data. So TT is actually K. Okay, so from K equals to 1 until K equals to 6,000. So this is the amount of data, the how many data that I have in the system. All right. Okay, then X and Y is also there. So you can see X and Y, that is the value. Okay, 6,000 data of X and then 6,000 data of Y. Okay, so I'm going to clear all these again. Okay, so that tick here is actually, I just want to estimate how long it takes for me to actually run this program, this least squared just now. So this is just a clock, a stopwatch to count my time. So when I want to use tick, I have to have that top there. Okay, so when I put tick, as if I'm going to start the stopwatch. Okay, and when it's finished running all this program, I'm going to put top at the end, so that it will actually count for me how long it takes for it to actually run that program there. Okay, all right, in this case I use number of parameters. So if you look at beta just now, inside beta matrix there are a value of A and B. So this is the unknown parameters. So if you have decided that the model order of your system that you want to use is the model order is equals to 5, n equals to 5. So the parameter that you're going to have is 10, because you have 5A and 5B. You have A1, A2, A3, A4, A5, B1, B2, B3, B4, B5. Okay, so you have 10 parameters. So over here, I put MP as the value of parameters. So if I put MP equals to 1, that means my model order is half of the number of parameter, which is 1. Okay, so sorry, this NP is equals to 2. So my model order is equals to 2 divided by 2, which is 1. Okay, so if I put here NP is equals to 10, so it means I have 10 parameter. Okay, so therefore automatically my model order is going to be 5. Okay, right. Phi here is actually the phi matrix. I just put a bracket and a square bracket and a closed square bracket. Why? Because I just define phi as a 0 matrix. Okay, it's a matrix, but the size is actually 0 in the beginning. Okay, even though I have 6,000 data, you've seen just now input X and output Y is having 6,000 data, but I'm just going to use, for example, 4,000, the first 4,000 data. I'm not going to use the whole lot. Okay, so it's up to me. I can use all if I like. Okay, but normally when I do system identification, I always like to divide the data into training data and also testing data. So I'm going to train the data using 4,000 first. Okay, so when I want to test the model that I have developed later on, I'm going to use the last 2,000 data that the system have not seen before. Okay, so have not been used during the training. Alright, so this is the loop that I have to write. Okay, I'm going to start for I is equals to MO plus 1. So I put the model order. So instead of starting with K equals to 1, I start with K equals to 1 plus N. Remember? Okay, so when I have K equals to 1 plus N, so MO is the model order plus 1. So this is how I start my iteration. So K equals to 1 plus N. So it's written here as 1 plus MO, which is the model order. And I'm going to run until end, which is the data that I'm going to use. I put N is equals to 4,000 here. So if it's 6,000 or whatever, this will change automatically. Okay, N minus MO. MO is our model order. So the only iteration that I'm going to use, I'm going to stop at N minus MO. So if I have 4,000 data and the model order that I use here is 5, I'm going to stop my iteration at 4,000 minus 5. Okay, so only 3,995. Okay, then I'm going to write my phi here. Phi is equals to I is K with all the value as defined in this slide here, in this row here. Okay, it is a bracket. I put a square bracket, negative Y starting with yi minus 1. So you see when I start with MO plus 1, so when we have that yi minus 1 is going to start with the value of MO plus 1 minus 1. So that's going to be negative y MO. MO is my model order just now. So it's similar to in the slide that I have earlier. Y here we're going to start with YM. Okay. So YM, then I'm going to have that Y. If my value of N is 5, that will be negative Y5. Okay. Then I put double dot and then negative. What does it mean? It will decrease in value. So if it start with Y5, it will decrease by 1. It will then go for Y4, Y3, Y2. Okay, so until when? Until I minus MO. So I is the number of iterations. So if I have model order just now N plus 1, so that model order will be I minus my model order again. So that I will be MO plus 1 minus MO. So that's going to give me 1. Okay. So what happens is that the iteration will stop until Y is equals to 1. Alright. So if I start with value of 5, it's going to be negative Y5. Next is negative Y4. Next is negative Y3. Negative Y2 until negative Y1. Okay. Similarly over here, I will have that for my U as well. Okay, you start with YU, sorry, U, not U, in this case I use X. Okay, we start with X, XN, okay, XN, in this case, let's say N is equals to, in this case is 5, so it's going to be X5, X4, X3, X2 until X1. Okay, then I close the bracket. Alright. Then that will be the loop. Okay, so when I put that in loop, I will generate phi. Of course I cannot write in by hand writing, it will be too much, isn't it? Because there are 4,000 data. You're not going to write in handwriting like you've done before in your in the previous video. We write using hand calculation. That's not going to happen, right? So we're going to use Matlab to do it. Okay, for y is quite straightforward. I'm going to just name y, my prediction y is, I'm just call it yy. It is actually equals to my output y starting from mo plus 1. So this is yn plus 1, okay, until the n data that I have. So this is actually the y matrix in our slide, okay. So then I just write for my least square estimation. This is my least square estimation. It's quite straightforward, isn't it? Okay, so my least square estimation is just beta. Beta is equals to the inverse of phi transpose multiplied by phi, okay, close that square, multiplied by phi transpose multiplied by y. So this is my least square estimation, okay. So when we write this least square estimation, it will actually estimate our beta. So the number of beta that we have is according to the model order that we have. Number of parameter that I estimated here, that I defined here. So if I say the model order is 5, so number of beta is going to be equivalent to number of parameter, which is 10. Okay, so we have A 1 until 5, then we have B 1 until 5. That is your least square estimation. As soon as we've done the least square estimation, we can quickly predict our Y. Okay, so we predict, I'm going to call my Y prediction as YP. YP is simply phi multiplied by beta. So what is Y phi? Y prediction, okay? Then we're going to get our error. Error is just Y multiplied by Y prediction, okay? And the mean square of error, okay, Matlab, it have this function MSE, okay? That MSE is actually calculating your mean square error, okay? So I'm just going to put that as my calculation for this program. So I'm going to put mean square error of the prediction error, okay. Then I'm just going to plot my y and yp, okay, the actual value and the predicted value. And for figure 3, I'm just going to plot my time and my error. Okay, let's run this and have a look how it actually perform. Okay, so when I click run, I will run this program here. Okay, so when I click run, okay, so immediately actually the figures have pop out. Okay, so I will show you later on the figures. It's actually have pop out. Okay, and then the mean squared error actually we have here is 2.2714 to the power of -4, which is very small. And the elapsed time, which coming out from our function tick and talk just now, it giving me the elapsed time or the time used to calculate this algorithm is 0.631 second. Okay, so you see, using Matlab, we use 4,000 data. We can calculate the least squared estimation within a very in a split second. It's not even 1 second, isn't it? It's 0.6 second. Not even, it's just slightly more than half a second, isn't it? Okay, so which is very fast, right? So just remember, when you did your assignment before, it took you a long time to calculate using 10 data, isn't it? It's a very long time for you to calculate your least square, but using Matlab, it is very fast. Okay, so let's have a look. How does the figures look like? Okay, so this is how it looks like. You see the figure 1. Okay, so it is actually for figure 1. It is actually the input. The blue color is the input to this system, and then the red color is the output to the system. So I use these both input and output, put in the matrix form, and then I predict the output, okay, using the Matlab programming that I've shown you earlier. Okay, so when we do the prediction, then you can see for figure 2, all right, for figure 2, you can see that actually there are two data there. Okay, two lines, the red color and the blue color, it is overlapping. So one of them is actually the predicted output and the other one is the actual output. You can actually find out which one is predicted output, which one is the actual output by giving some legend to this plot. You can just simply add the legend if you like, okay, by using the insert that you have here. You can simply add the legend Okay, then you can tell which one is the predicted output and which one is the actual output. In this case, it's actually a very good prediction because the graph is actually overlap between one another. All right. Okay, the last figure that we have here is actually the this is actually the error of the prediction. So you can see that the error is very small, is it's around 0. Okay, but there are some point where it's predicted with a higher error than others. Okay, and then of course for the error, it's very difficult for us to find out the error because we have 4,000 data. Okay, so what we do is we find one value, which is the mean squared of all the error. Of course, the less mean squared that you have, the better your prediction for your least squared estimation. Okay, so let's have a look again. I'm just going to run again with the different model order just to show you how does it look like. Okay, so let's go back and have a look what happened if I change the model order. Okay, instead of having model order 5, what happened to it? Okay, let's have let's say maybe I change this to 4. So if number of parameter is 4, means my model order is half of it, which is what? Which is 2. Okay, the data I'm just going to use again 4,000, no problem. Okay, I'm just going to have a look what happened when I run this. Is it going to be better or not? Is it going to be better than 2.27 times to the power of minus 4? When I click run, it immediately give me my result, and it's quickly actually popping out the plot. Okay, but you cannot see here. I haven't because it is in the at the back of this slide. Okay. Alright, so the mean squared error is 7.44 to the power of minus 5. This is even better, isn't it? So it's not necessarily that you have higher model order, the system will predict for you better, isn't it? So in this case, you see that a lower model order actually giving you a better prediction. Why? Because maybe your actual system is having model order of 2. In this case, we are using model order of 2. Okay, so when the prediction is very close to the real system, the prediction error will be less. Okay, so it's not necessary that we put higher order, it will solve our problem. No. Okay, so it depends on our system. So in this case, maybe the actual system is maybe having model order of 2. So that's why our model order is actually better. The prediction error is better when you use model order of 2. Okay, and you can see here the elapsed time is 0.5, which is faster actually to predict. Okay, let's have a look how does the response looks like. Okay, so alright, so this is the how the response look like. Okay, again the figure 1 is the actual input and output, figure 2 is actually the predicted output and the actual output. So you can see that the blue line is actually hiding behind the red line even more. Okay, because the prediction is much better, and also the error that you have here is also much better. Okay, because the mean squared error is less than before. All right, so that's how we do our least squared estimation using our Matlab programming. So what I'm going to do next is I'm going to show you how to come up with recursive least squared. So I'm going to show you that in the next video. So for that, thank you very much. Goodbye.